So now that we've kind of looked at relative acid-base strength, we need to come up with some kind of convenient scale in order to express this. But before we get to that, let's talk about the autoionization of water. So if we have a reaction here that we can express as H2O liquid plus H2O liquid in equilibrium with H3O plus OH minus, we can kind of examine some of the conditions of water. For example, H3O plus is an acid, OH minus is a base. Okay, so that means that we have these conjugate acid-base pairs. So if we have an acid here, that means that one of the waters has to be a base, the other needs to be represented as an acid. And based on this, we can say that water is amphiprotic, meaning that it can act both as an acid and as a base. Okay? We can come up with an equilibrium expression for this particular reaction. So if we wanted to come up with K, we can say that our K is going to equal the concentrations of the products, which is going to be H3O plus times OH minus, divided by the concentration of the reactants, but our reactants are all pure liquids, so we're just going to divide that by 1, or we're going to say this is our K. We have a specific value, this is going to be a specific K that we're going to refer to as Kw, which is equal to the concentration of H3O plus times the concentration of OH minus. We can also write this, and a lot of the times chemists are kind of lazy, so they don't want to write out that H3O plus in full. So we can say that this is going to be the concentration of H plus times the concentration of OH minus, and this is experimentally determined to be 1 times 10 to the minus 14. Okay, so this is going to be our Kw expression, which is going to allow us to kind of compare the strengths of acids and bases. So if we have a neutral solution, our concentration of H plus is going to equal our concentration of OH minus, and both of those are going to be 1 times 10 to the minus 7. If we have an acidic solution, our concentration of H plus is going to be greater than our concentration of OH minus. And if we have a basic solution, our concentration of OH minus is going to be greater than our concentration of H plus. So this will, Kw and knowing some of this stuff will allow us to calculate the concentration of H plus when we know the concentration of OH minus, or we can calculate the concentration of OH minus if we know the H plus. So for an example of this, we're asked to calculate the concentration of H plus when the concentration of OH minus is equal to 1.0 times 10 to the minus 5. Remember that the concentration of H plus times the concentration of OH minus is going to be equal to 1.0 times 10 to the minus 14th. This is going to equal the concentration of H plus times 1.0 times 10 to the minus 5, which was given for our OH minus. So our concentration of H plus is going to equal 1.0 times 10 to the minus 14 divided by 1.0 times 10 to the minus 5, which will equal 1.0 times 10 to the minus 9. So in this particular case, if we compare these two, our concentration of OH minus is 1.0 times 10 to the minus 5. Our concentration of H plus is 1.0 times 10 to the minus 9. So that would make this particular solution basic, because our OH minus is greater than our concentration of H plus. So to kind of recap what we have in this video, we talked about the autoionization of water, and that water is amphiprotic, and this allows us to come up with an equilibrium expression to relate the concentration of H plus to the concentration of OH minus. And we can do specific example problems from this And this is going to lead us into something called the pH scale, which will be a convenient way for us to represent the acidity of various solutions. And we will cover that in the next video.